All right, let's get started. So I have posted a reading for this unit, but the relevant material from that reading is only 9 pages, which, less reading isn't necessarily a bad thing. But the reading isn't really, it's not focused around this week's content or last week's content. I mean, it is, but there's a lot of other stuff that we will cover later on. So it's not the best reading. I wish I had found something more comprehensive. I'm still going to be looking, but everything that I found goes through stuff in the sequence that I think is not the best. So anyway, this is what I found. I'm going to continue to look. It could be that for this 2-week period, we just don't have a reading that's quite ideal. I've also posted a bunch of readings for the next unit, which is very closely connected to this one, but I decided to make it its own thing. I've also posted a more focused reading for that next unit. So that's all up there, and I'll continue to let you know when I'm expecting you to do the readings and which readings cover which content. Also, obviously, the course evaluation went out last week. This is the last time I'm going to ask you to do this. Please do this. It really helps me. It also will help future iterations of this course, regardless of whether I'm teaching it, since we did really change a lot of things. And I am particularly interested in this course evaluation because we went through a couple of units on data management, philosophy of science that were entirely new. And so I'm really curious to get your feedback about it, what they were helpful, what we could change to make them more helpful. If you just thought they were useless and would prefer something different. I'm just interested to hear your thoughts about that. So that would really help me a lot if you did that. All right. So today we're going to be working with a slight variation of the same problem that we've been running through with the review pictures unit. We're still working with grant evaluations, but the structure of the data set has changed yet again. So before, each person was reviewing 2 grants. Now each person is reviewing 4 grants. In addition, we have an extra variable to consider. So we still have grants that vary in quality. Some of them are lower quality, some of them are higher quality. But in addition, we're varying who the submitter is presented to be. So you can imagine that what we're doing with these grants is that some of the grants, the principal investigator is called the main person who's in charge of the grant. His name is John Smith, and for some of the grants, the submitter with his name something like Jane Smith. So we're varying the apparent sex of the principal investigator. The outcome is still the same. And I guess let me ask you, so based on this design, what are some research questions that might be of interest to someone who has this kind of data set?
Males and females rate grant quality differently?
So yeah, we look for sex differences, but we're not looking at the sex of the rater. We're looking at the sex of the person who appears to have submitted the grant. So we have grants, and sometimes the main scientist behind the grant is named John Smith. Sometimes they're named Jane Smith. That's meant to convey that the submitter has a different sex. And we can look for whether people evaluate the grants with the DI named Jane Smith differently from the grants with the DI named Jane Smith. So yeah, very close, but before we were looking at the evaluator side of things, now we're looking at the evaluation side of things. What else? What else could we What other questions could we ask? I can be patient. So we've got grants that vary in quality, grants that vary in who appears to submit grants.
We do grants within like gender. So like female, male, see if they did better within the group.
See if who did better within the group.
A male did better, like see how many males did better than the other males.
So we could look at whether some males fared better than others, and what would be the other variable that we would be examining.
Quality of the grant?
Yeah. So did males who submitted higher quality grants get better ratings than those who submitted lower quality grants? So that's one. That's another question we could ask. What else?
Well, it seems like you've got an interaction situation going on.
Sure. So what would be the question that would go along with that interaction?
You look at are the ratings for low and high quality grants different depending on the gender of the submitter grant?
Sure. So did the gap in ratings that low and high quality grants receive vary by the sex of the submitter? So maybe there's a smaller gap for males or a smaller gap for females. Or another way to frame that is, did the sex difference vary according to the quality of the grades? So is it larger, say, for high quality grades than for low quality grades? Absolutely. Anything else?
If there's an interaction between the evaluators and like the gender of the evaluators and the gender of who submitted it.
Yeah, absolutely. So if right now in this data set, we don't have the sex of the evaluator, but we were just working with that last week. We added that back in. We could look at that kind of difference. I'm not going to go quite to that level of complication today, but absolutely that would be an interesting question. There's also the question that one of the questions we were focusing on last week. Did the high low quality grants just overall get different scores? So a couple of questions that could go along with this design. Is there a difference in ratings based on the quality of grants? Is there a difference in ratings based on who appeared to have submitted grants, who was the lead scientist? And something like, does the size of any sex difference that we see vary by grade quality? So this is what this data set looks like. Now, remember one difference in this data set as compared to the data sets that we were working with last week is that whereas before we had 2 rows per evaluator, 2 rows per people who scored these grades, now we have 4. So these 4 rows, for example, belong to participant ID number 1. So before, of course, I made this point about how we had one variable that varied within units within raters. Well, we still have a variable that varies within raters. So quality dichotomous, that's that quality variable. So half the grades that these raters evaluated were low quality, half were high quality. What's different is that, as compared to last week, is that we have a second variable that also seems to vary within raters. So the raters evaluated some grants by female PIs, some by male PIs. And in fact, in this particular study, there was exactly half female grants and half male grants. So this data set has a different structure than the one we were looking at just last Wednesday. Last Wednesday, we had a variable that did vary within participants and a variable that didn't. Here we have two variables, both of which seem to vary within participants. And of course, the thing to ask yourself if you're trying to figure out does something vary within participants is if I take just a very small, think about like one very small data set just for participant one, so just for those 4 rows. Does the variable that I'm working with change within that miniature data set, or is it the same within that miniature data set? If it changes, you've got a variable that varies within that unit within rater. Kind of makes sense. That's called that. And that's a sign that that variable maybe ought to be considered what's called a rater effect. It ought to be treated as in this first stage of analysis where you're breaking apart the data set to these chunks. You do a little regression on each chunk, and then pour everything over to the second stage. So this is, again, this is a different structure. Before we only had one variable that went into that first stage. Here we have 2. So in this first stage of analysis, of course, what you're doing is you're figuring out some sort of little miniature regression equation that you're going to apply to each chunk of the data set. Each chunk is defined by one participant. So we have 50 raters here. We're going to work with 50 subsets of the data set. We're going to apply this miniature regression equation to each of those subsets. And the hypotheses that we are probably interested in testing also probably involve interactions. Thinking back to those research questions that we might be interested in. Some of the research questions are about just the quality difference. Some are about the sex difference, and some might be about whether the sex difference varies by quality. So when we've worked with this kind of problem before, this is the kind of model that we've usually worked with. The outcome variable is a function of an intercept. That's that A sub 0. Quality effect, that's that A sub 1. A sex effect, that's that A sub 2. And in this case, I'm also adding in an interaction term. So that's A sub 3, which corresponds to sex times quality. So, okay, very similar kind of model that we've worked with many times in the past. You've got 3 different variables. One of them is just a main effect, another is another main effect, and another is an interaction. It's just that we're applying this model to to 50 different subsets of the data. So we're breaking this data set apart into 50 chunks, applying that model to each of those chunks, and then extracting out some rater estimates from each of those chunks. Does that make sense? So based on this process of breaking apart the data set into these 50 different chunks, you might extract out a bunch of different intercepts. That's that first A sub 0 term in this regression equation that we're applying to each of these chunks of the data set. That gives you 1 intercept per participant. So we have 50 participants, that gives us 50 intercepts. So that looks similar to what we were doing on Wednesday. We're also going to extract out a bunch of different slopes for quality. We had that slope for quality before, because we still had that quality manipulation back on Wednesday. So that's true here. We're going to also extract out 50 slopes for quality, 50 quality effects, 1 quality effect per review. This part is a little bit different. So before, we were only working with 2 of these parameter estimates that we got for each participant. Now we've got at least 1 more. We've also got a sex effect for each participant. So this is a new parameter that we're extracting out for this process of getting these little miniature regression equations. And then this last term is also new. So before we weren't thinking about any interactions at all. Now we've got a bunch of interaction terms as well. 1 for each reviewer, yielding 50 interaction terms. So what's new here is basically these last 2 terms. Before, we were only working with these like sort of 2 parameter models that we were fitting to each subset of data. Now we've got 4 parameter models that we're fitting to each subset of data. And that gives us 4 individual terms to be analyzed in that second stage. We're thinking about that second stage of analysis, so we've extracted out all of the individual terms that we're interested in from each subset of data. Well, we don't have anything besides intercept in the second stage. So last week we were dealing with a case where we did have an extra variable, so the rate intercepts. Now we're dealing with a case where we don't have an extra variable in that second stage. All we're doing is we're sort of calculating an average across each of these 4 columns. So just to summarize, what's different with this model as compared to previous models that we've worked with is that we're adding in a little bit of complexity on this first stage. But in the second stage, we're still dealing with a pretty simple case. We don't have any extra variables. All we're doing is we're taking an average across each of these 4 new extracted variables. Any questions? So what I just showed you is this 2-stage process that I introduced last week. In that first stage, you fit some sort of regression equation, 1 per unit that you have, and that gives you a bunch of different parameter estimates that are a little bit different across the different units that you have. So we're dealing with reviewers. Each reviewer gets their own set of 4 parameter estimates. And in the second stage, you fit an overall model across each of these extracted values that you have. So we have 4 extracted values. We fit the same regression equation to each of those extracted values. So what this gives you is we have a slightly more complex structure that corresponds to that first stage of analysis, where you're fitting that little regression equation to each participant. Before, we only had quality. Now we have quality, the sex of the PI, and the interaction between quality and the sex of the PI. That, of course, is called the random effects part of our model. The random effects are the things that can vary across whatever unit you've got after this straight line. And indicate that we want to take these averages of each of the effects that we have in here. We add this part outside of the parentheses. So this just says, for each of the effects that you have inside the parentheses, we're going to take an average. And that part is called the fixed effects. So first stage is the random effects. It's the stuff that can vary across units. The second stage is called fixed effects. The fixed effects are the things that are the same for everybody. Everybody contributes to one average, but you only get one average. It's the same for everybody. Okay.
I don't know if I understand the language of that. Quantities of interest from stage one as the outcomes. And what do you mean by this?
I mean that you can sort of think about getting the second data set. So the first column are all of the individual intercepts that you get. The second column are all of the individual quality effects that you get. The third column is X effects. The fourth column is interactions. And you can sort of think of using each of these columns as its own individual outcome in that second stage. So each time we're getting a very simple model where we just have an intercept and some error.
And that's behind the hood, like more.
That's, yeah, that's, all this is part of what's happening when you make that call to element that new function that I talked about last week. Is that fair? Other questions? So let's see what this process looks like graphically. So one difference as compared to last week is that last week we were only dealing with pretty simple cases, relatively simple cases. This is kind of hard conceptually. So if it's taking a while for things to click in, don't worry. This is like something that's really new as compared to what we've done before. But anyway, last week we were dealing with cases where each unit only gave you 2 scores. So each person rated a grant that was low quality and a grant that was high quality. But this week, we saw that each participant had 4 rows. They give you 4 individual evaluations. So what I'm showing you here is one sample participant. Notice that if I plot, say, quality against the scores that this person gave us, we have 4 scores instead of 2, or instead of, say, 1, which is what we always dealt with before we got to this unit. So we've got 4 scores to deal with. And, in general, our statistical methods like it better if we have one quantity that we're analyzing instead of multiple. So let me show you what it looks like graphically to go through this process of calculating these individual quantities. So the first thing that I need to do with this one participant's data is I need to get some information about the sex of the submitter, the sex of the PI. So I have gray dots here, but one way I can get that information onto this graph is I can color code those points. I can make the grants of the male PIs one color, the grants of the female PIs a different color. So that's pretty familiar. That's something that we've done with a lot of these statistical models when we've been trying to get multiple kinds of information onto these graphs. So that's all I've done. I've made some of the points for the male PIs blue and points for the female PIs this reddish pink. So that's it. That's one stage in order to get this extra information onto the graph. So one thing that's different about this kind of model as compared to the models that we were working with last week is that we have lots of different quantities that we might be interested in from each individual participant. In fact, there were 4 different things that we got from each participant. So one of those things is the sex difference. So that is the average difference in the ratings given to the male grants versus the female grants. So all I've done is I've drawn 2 horizontal lines, one that represents the ratings for the average rating for the female grants, and one that represents the average rating for the male grants. And I wanted to understand for this one participant, what was the average difference between the ratings for male grants versus female grants? How would I get that information from this graph?
Check them, their intersects.
It's just the vertical distance between these 2 lines. We've worked with this kind of graph before quite a bit, and often one way of understanding, what is the effect of one variable, for example, is to look at this vertical distance.
I think something just clicked with me. So each reviewer receives a high and low quality grant for the male and female submitter.
Yes. So
So you get four different grants too.
that's absolutely right. So going way back at the beginning, I had 4 different scores that each person is giving me because they're evaluating 4 different grades. So this is a major difference as compared to the example that we were working with, or the examples that we were working with last week. Last week we were working with a case where each person gave me 2 scores because they rated 2 grades. Here they're giving me 4 scores because they're rating 4 grades.
Yeah, thanks. I missed that earlier.
Yeah, how's everybody else doing? So just to make sure that we're carrying the thread through, that's why if I'm trying to represent this kind of example using this data set, each participant gives me 4 rows because they give me 4 ratings, 1 for each grade that they rated. Okay, that's how I'm able to color code these points for one participant. This one participant, even though they're just one person, they gave me 4 different ratings. And the ratings varied in whether the grant that they were rating was low quality versus high quality, and in addition, whether it was a female PI or a male PI. So one of the things that I'm able to do is find out, well, based on the 4 grants that this person rated, what's the average difference between the ratings they gave to female PIs and the ratings they gave to male PIs. So that's one of those quantities that I talked about when you're getting these mini regressions. So what's another quantity that we were talking about with respect to this problem where we have 4 grades? What's another piece of information that I could add to this graph that tells me something about how they behave to this experiment?
interaction ones?
Um,
Like on the graph currently?
yeah, so what's one extra piece of information I could add to this graph that tells me something about how this person behaved in this experiment?
Slope of the quality one?
Yeah, so that's another piece of information I was interested in. Another piece of information I extracted out from each reviewer is what ratings do they give their low and high quality grades. So here's what that sort of information might look like. This is the average rating given to the low quality grades, and the average rating given to the high quality grades. Notice how this also looks very similar to more complicated graphs that we worked with when we didn't have to think about, each person doing multiple things. It's just that right now, it's applied to just this one person, just these 4 groups. What's one extra piece of information I could add to this graph that tells me something about how this person behaved?
I think Morgan already said this, but the interaction between quality and gender.
And how would I represent the interaction on this graph?
Different, it would have to be 2 different lines to represent 2 different slopes. So like female, high and low quality, and then a line for male, high and low quality.
Absolutely. So what I could do specifically is I could just connect the lines of the different colors, or connect the points of the different colors. So I have one line representing the rating difference given to female versus male quality grades or female versus male grades that differ in quality, and another line representing the ratings given to male versus male grades of different quality. So I've got 2 quality differences, one for males and one for females. And when we've worked with interactions in the past, this has been a very familiar piece of information on these graphs. We've often looked for lines that difference in their slope. So similar principles, but instead of being applied to everybody, they're just being applied to these 4 points for this one reviewer. Okay, so this is one single reviewer, but we have 50 reviewers. We don't just have one reviewer. So what I'm going to show you next is the same information, but added to each of the plots for each of my 50 reviewers. It's going to be a lot to look at, but just think about building up this process each time, 1 per reviewer, to give you 50 times. So here are those 50 plots. I've labeled each plot using each person's participant ID. And on each of these plots, I've got 4 points, because each reviewer gave ratings for 4 different grades. So the first piece of information that I added to these plots was I need to be able to tell which of these points belong to female PIs and which of these points belong to male PIs. So all I'm going to do is I'm going to mark these points with different colors. 1 color for female PIs, 1 for male PIs. It's a little bit hard to see, but you might be able to see that these pinkish dots, those are for the female PIs. The bluish dots are for the male PIs. This is just that same process that I applied to that single plot, but now I've applied it to all 50 of these plots. So the next piece of information I added to these plots was you might want to know something about the sex difference. So did each reviewer give a different rating to the male PIs than they did to the female PIs? So to get that information, I can draw two horizontal lines, one for the male grants and one for the female grants. And this is what that looks like. One thing I want you to notice is that the sex difference in ratings is not the same for each person. And that's because I'm allowing these sex differences to be different across reviewers. Each reviewer gives me a slightly different sex difference because they responded to the sex of the PIs in a slightly different way. The next piece of information that I added to that individual graph was information about quality. So each reviewer responds to the quality information of the grants a slightly different way. Some reviewers might give a much better rating to the high quality grants. Some might even give a better rating to the low quality grants. So what I'm going to do is I'm just going to draw a single line that represents how each of these people responded to the low versus high quality grants. Another thing that I want you to notice is that just as each person responded differently to the sex of the PIs, each person responds a little bit differently to quality manipulation. For some people, this line has a positive slope, for some it's a negative slope, and for some it's about a zero slope. So the last piece of information I added to these plots was information about the interaction. So whether, say, the sex difference, the difference in ratings we gave to male versus female PIs is different for high versus low quality grades. So I'm going to add two extra lines here. Each line is going to connect the points from a single color. One thing that I want you to notice here is that each reviewer had a slightly different interaction term as well. So the thing to look for is whether these lines are parallel or whether they have different slopes. And for some people, they're exactly parallel. For some, the lines are pointing in, and for some, the lines are pointing out. So okay, I just want to emphasize here, this is the same process that I went through for one reviewer. What I'm showing you now is that I can go through that same process for each of my 50 reviewers. They're going to give me slightly different quantities for each of these different terms. How would it? So I could have shown you one of those very complicated plots where I have like lots of connecting lines, lots of horizontal lines, getting all of those quantities on one plot, but it gets to be really busy. So what I'm showing you right now is a plot that looks highly similar to when we first worked with interactions last semester. They also did quite a bit in our contrast unit. We've seen a lot of plots like this where we have some points in one color, some points in another, and something on the x-axis. What I could have drawn, which makes this example slightly different from other examples that we've worked with, is each of these individual slopes connecting a point from each of these groups of points. And I want you to imagine as if I had, because that's really what our model is saying, is that there's some meaningful linkage between the points in each of these different groups. That linkage is what I was showing you with these individual plots. It gets to be really busy though on this main plot. So even though this example is highly similar to other examples we've worked with in the past, there's that one slight difference, and that's that there's a meaningful link between the points that one reviewer tables. We have these groups of 4 points that have some sort of linkage. That linkage is they came from the same review. So I go ahead and fit this model using that new function Homer. This is the results that Homer gives me. And one thing that's unique about Homer is that by default it doesn't give you p-values, so you have to use the calculate ANOVA function in the car package. But anyway, these are the results that you get from Homer. So if we were to consider that first row, the intercept, how might that first row be represented on this graph?
Just red black line crosses the dotted line, like ranging cross quality integer.
Yep, it's the place where the black line crosses the dotted vertical line. And it's the overall average rating given to all these different grades. If you were to use the intercept at 3.14 in a sentence, how much you describe what's going on?
The average overall impact across all of them.
Yeah, and it's specifically that average value is 3.14. I know I've said this a couple times, but just to hammer this home, that is the same kind of interpretation that we give to any sort of intercept. It's the predicted value at 0 in all of our predictors. 0 on quality represents the average of high and low quality. 0 on sex represents the average across male and female grades. So this is the overall average rating given to grades and stuff. Okay, what about this next row? So first of all, how would this next row be represented on this graph?
With the slope of the black line?
Yeah, absolutely. It's the slope of the black line. And just to reemphasize this is the same place where we've looked for similar quantities on graphs like this. The slope of this black line represents the average quality, the average difference in ratings for high and low quality grades. If you were to use that minus 0.73 in a sentence, how might you describe what this minus 0.73 is telling?
high quality grants are rated 0.72 units lower than low quality grants, which means they have a higher impact.
Yeah, so one is a better score. Higher quality grants are rated with 73 units better than low quality grants. Absolutely. All right, what about this next row? So remember, this is the sex of the PI. So first of all, how might this number be represented on this graph?
The difference between blue and pink line at the dotted line.
Absolutely. So it's this difference right here, the vertical distance between these two lines. It's very similar to how we've interpreted other graphs of this type. And if you were to use this minus 0.45 in the sentence, how might you describe what this minus 0.45 is telling you?
Male grants are rated better on average across quality.
Yeah. It looks like we're seeing maybe, it's not significant, but maybe a little bit of gender discrimination. The grants of the male PIs are rated a little bit better than the grants of the female PIs.
Can I ask you a question?
Yeah.
So on this, on the last slide, when you had each individual one, it kind of seemed like the female submitters had higher impact ratings across each of the.
Yeah, so it's possible that I screwed up the colors, so I can double check that. But what we literally are doing, just to be very clear, is we're taking these vertical distances for each person, and we're taking the overall average. So those two things should match up. I'll have to double check. It's possible that I made an error with my coloring. But yes, you are absolutely right. If you're seeing, if it looks like, the individual vertical distances are going one way, that should be reflected in your overall analysis.
Something to look out for, I guess, if you go through this and accidentally mix up your colors.
Yeah,
you start
learn from me. Don't make the mistake that I did. Well, each time I have to do a lot of preparation, and obviously I make mistakes sometimes. But I'll double check that and make sure that they match up. What about this last term, the sex by quality interaction? So first of all, where might this be represented on this graph? Or how might it be represented on this graph?
This is the interaction.
It is.
So is the difference between the two lines just the slopes of the two lines?
Absolutely. So one way to think about it is that it's the difference in slopes between these two lines. There's another way you can think about it. Anybody remember what that other way is?
Difference in vertical distances between red and blue lines.
Take the vertical distance here, compare it to the vertical distance here. Absolutely, great. And if you were to use that that value in a sentence, so the 0.42, how much you describe what's happening in the context of the problem? And if it helps, remember that this is the line for the female PIs, this is the line for the male PIs. So you can use the the graph to assist you in thinking about what's happening here.
Kind of looks like the gender difference is smaller for high quality grants, or the gender difference in the rating of the impact is smaller for the high quality grants than for low quality grants.
Yeah, so this isn't a significant difference, but this might, if we had much more data, let's just assume that we're not have yet unlimited data here. What this might be telling us is where gender discrimination is happening. It's happening more with low quality grants than with the high quality grants. Specifically, this is telling us that the sex difference is 0.42 points more towards zero among the high quality grants than among the low quality grants. Or another way of thinking about this is that for males, the quality difference, or the difference in ratings given to high and low quality grants is not so strong. But for female PIs, they get a little bit of a penalty for those low quality grants.
Male, negative 1.5.
Yes. Question?
So how do you know that is this like whenever you say a 1 unit increase results in these changes? Like how do you know it's male or female? That's higher or lower?
So often when I show, well, when I'm actually interpreting these, I mean, I do sort of check to make sure that my coding scheme is the way I expect it to. So I guess I do make sure that these two pieces of information are consistent. But often what I'll do is I'll think about the graph, think about what the graph is telling me. Well, it's telling me that the slope is more towards zero, the slope is more negative. And that might help me understand what the interaction term is. You can also literally go back to your coding scheme, see, oh, I coded males minus 0.5, females positive 0.5. So those sex differences tell me, for example, did females score better, so positive number, or worse, so negative number. And then I might see, oh, you know, I coded low quality grants minus 0.5, high quality grants positive 0.5. So this interaction term is telling me, how did that scoring difference change as I go from low to high quality grants?
Right. So in this case, when you go from male to female, low to high quality, it gets worse.
Correct. So you do have to go back to your coding scheme. I like to set up my coding scheme in ways that I find intuitive. So if I'm having trouble thinking about what my results mean, I might go back and recode everything just so that it helps me think. I do like to look at my coefficients, and obviously I like to look at my coefficients and think about what they mean. I think it's a helpful thing to do. One thing you can do to help yourself is code things in a way that's intuitive.
Maybe also do it the same way every time too.
Yes.
Don't think about it too much.
Going back to the data management unit, I have certain standard ways of handling certain types of problems. Keeping that standard is a good way of making sure that if you fall into a mental habit, you're not working against the mental habit.
So,
good one.
in this scenario, would you report the interaction in the grant seg since they're like, geez,
Well, yeah, so
make it no?
I would say that's not significant. I mean, it's just not significant. Right now, I'm for the point of just like interpreting what that coefficient means. You know, you can just describe what it means. It is what it is. Whether or not it's significant doesn't change what you found in the sample. What p-value tells you is whether you can reject the null hypothesis, whether you can make an inference from your sample to the population. So, like a p-value doesn't change what this coefficient is. coefficient is the coefficient. What the p-value changes is whether you're permitted to make a certain inference to the broader population. Does that answer your question?
Thank you.
So last week, I introduced this idea of how you can think about this kind of problem in a slightly different way, sort of taking a series of different scores and doing analysis on those different scores. So let's see what that looks like in the context of this problem. So this is what we just did. We have this data set in what is often called long format, or also called tidy format, where they're allowing multiple rows per reviewer participant. But I could change the format of this data set, put it into what's often called Y format. So specifically, I could take that data set and try to get it so that each row corresponds to a single reviewer, and each reviewer has no more than one. So in order to do that, what I need to do is get some information from this data set up into the column headers. I need to use that spread function. So spread takes a single column, and it spreads it out across the rows, and it makes it so that my data set is shorter and fatter. But I have two variables that I want to do that with. So both of these variables vary within reviewers. If I just took quality and put it in the column headers, well, I'd still have the reviewer, or sorry, the graded sex, the PI sex, that I also need to get into the headers. So the first step to getting this into Y format, this different format, is compressing these two columns into one single variable. So what I did here is I created a new variable called condition that's a combination of quality and PI sex. Notice I put an underscore here to indicate, hey, I'm indicating one thing, so quality, and then the other thing, which is PI sex. So this single column has 4 possible values: low underscore male, low underscore female, high underscore male, and high underscore female. It's that combination of 4 conditions that we have for this problem. Does everybody follow what I'm doing here? So in the data management unit, I mentioned how we often or sometimes get into the situation where you have to, one column that is a combination of 2 variables. Here we're actually transforming our data set to make sure that that's the case, to illustrate another way of thinking about this problem. So I'm just compressing this long format data set now. I'm dropping those 2 columns that are PI sex and quality separately, just to make this a little bit easier to see. So the next thing that I can do is use the spread function. Spread, again, takes information that used to be in a column, and it puts it in the column names. It puts it in the headers. So I'm representing a variable in my design, but as column headers as opposed to a variable. And the spread commands that I do to get this into Y format is actually pretty simple. It's just spread, key equals condition. Key is the thing that's going into the headers. Value equals impact score. Value is the thing that's going to stay as basically numbers, elements, data.
How do you make the condition variable? Do you use mutate?
Yeah, you could use mutate and then a combination of, or you could use case when, case underscore when, or if else. We have these different functions that do one thing, one condition is met, or another thing, another condition is met. So you can use one of those. And what you're checking is very explicit. I have the code on the next slide, but just like I said, to be very explicit, you're checking, okay, if quality dichotomous is minus 0.5 and grant underscore sex is minus 0.5, I'm going to give that a low male. If it's minus 0.5 and 0.5, low female, et cetera, et cetera. Yeah, formulas. So this is this chunk of data represented in Y form. And what I want to draw your attention to is that we have 4 columns now. Each one is labeled by a certain condition. And what these numbers now represent is the rating that participant number 1 gave to high quality female grants. This is the rating to high quality male grants, low quality female grants, low quality male grants. So this is a different way of representing the same data. So just as a refresher, what's one piece of information that I might want to know about this problem? Like what's one quantity that might be of interest scientific?
Ratings for male and female.
Great, so the average difference between males and females. And if you wanted to know that quantity in this data set, what might you do in order to calculate that quantity?
I guess just create averages and differences.
Just a t-test, right? Doing a high female and low female.
Well, we have to calculate something before we can do, so we can't do a t-test exactly because we need, if that were true, we'd need a column here called, say, sex, and then a number over here. But that's not what we have. We have multiple columns, and the quantity that we want to test is composed of some mathematical operation that we do with these 4 columns. So what's the mathematical information that would tell me the average difference in ratings given to males versus females?
Would you not just average the female ones together and males together and subtract it?
Absolutely. So first you have to take the average of these 2 columns, then you take the average of these 2 columns, and then you take the difference between the averages. What's another quantity that we might be interested in that we could get out of these 4 columns?
Difference in grant information.
Great. So we could take,
Yeah.
perfect. So we could take a different set of averages. We would take the average across males and females for the low quality grants, the average across males and females for the high quality grants, and take the difference of those 2 averages. What's another quantity that we might be interested in? It's goddamn sales calls. What's another quantity that I might be interested in?
The interaction between sex of the submitter and quality of the grant.
Great. And how would I calculate that?
You could do high, average high.
Interactions, remember, are you can often think of them as differences of differences.
Yeah, I don't know.
you did those columns, right? High female, high male, or high female, low female.
Yeah, absolutely. So I could take the sex difference among high quality grants and then subtract out the sex difference among low quality grants. So this difference minus this difference. Or alternatively, I could take the quality difference among females and subtract out the quality difference among males. So these two columns minus these two columns. There's actually one other quantity that isn't necessarily of interest in this problem, but sometimes is of interest. Can anybody think what it is?
The difference is within for each participant.
Which differences?
Like for each participant, you could get each of those three things for each time.
Yeah, absolutely. So we have three things, and then there's often there's one other quantity that might be of interest sometimes. I could take just the average of all four columns for each participant. So that would be the intercept. So those are all of those four parameters that we started with when I talked about taking those individual regressions for each participant. We had an intercept, sex effect, quality effect, and the sex by quality interaction. I can transform my data set into wide format and do a little mathematical operation that gets me each of those quantities in a new column. So here's that intercept. It's the grand average for each participant, the average of those four columns. Here's the quality effect. I could average together across grant sex and take the difference in those averages for low versus high quality grants. I could take the average across quality within sex. So one average for females, one average for males, and take the difference between those two averages. And I could take this difference of differences. So the difference, sex difference among low quality grants versus the sex difference among high quality grants. So notice how these different operations match up exactly to those individual quantities that we extracted using our regression equation. This is another way of thinking about what those individual discrete regression equations are doing. They're doing these little mathematical operations. It gets me four different columns. And then I can take each of these four different columns and do the second stage of regression on each of the columns. So specifically, I do fit a little one thing in the model, the intercept one model, one for each of the new columns. I'm not going to go through this code in detail, but I'm just doing the things that I said that you could do. So you can use this spread operation, the spread function, calculate a bunch of averages and differences, which gives you four new columns. And then you could use LM 4 times, one for each column. And notice how the values that you get from LM in this particular example exactly match up with the values that you get from LM. This is just to show you that in this particular example, this is an alternative, exactly equivalent way of representing this problem. So one way of thinking about what you're doing when you're analyzing repeated measures, at least in some special cases, we'll get to cases that you can't analyze in this way with it, is that you're literally doing little mathematical operations. You're taking averages and differences and then fitting a series of models on those averages and differences. So this is that quality difference. Again, it exactly matches up. The sex difference, it exactly matches up. And the interaction, again, it exactly matches up. Okay, so what I showed you today is how to incorporate in extra information that's also extra variables that also vary within units. So we actually started with a model that had one variable represented within units. Now we added an extra variable that also varies within units. And I showed you how it's all you're doing is in that first stage of analysis, you add in those extra variables. And the way you modify that regression equation in that first stage works exactly as you modify a regression equation in any other model that we fit. So I could add in interactions, I could add in extra covariates. If I wanted to, I could do polynomial regression. All those extra things that we've done in other models that didn't have repeated measures, I can also do to that first stage of analysis. We're fitting these little individual participant problems. One thing that will change if you have extra variables that vary within units is that you have to have extra observations too. So I could have 4 observations from each participant in order to fit this model. You can imagine if I don't have some of those extra observations, I mean, I can't know like what's the quality factors for a given reviewer because it's just, I don't have the data to estimate that. But otherwise, this process, it looks really, really similar beyond this extra complication of having 2 stages, as it would in other models that we work with. And we saw last week how you can also add in variables that do not vary within units. The only thing that you change is that you change that model that you fit in the second stage. So variables that vary within units, you modify the first stage. Variables that do not vary within units, you modify the second stage. Another thing that changes, if you want to think about the same problem in a slightly different way, is you're doing these little difference scores on that wide format data set. While if you add extra variables that vary within units, you add extra quantities that you calculate, extra columns that you calculate when you're creating those little averages and differences. That's it. That's how you handle variables that vary within units. So on Wednesday, I'm going to talk a bit more about the design implications of getting things that vary within units. So far, I've been mostly focused on like how do you get this stuff in R. On Wednesday, I'm going to add in some extra information about why you might do this and what are the implications of doing it. What does it mean for the inferences that you make? What does it mean for things like statistical power? And also talk a little bit more explicitly about how to graphically represent those kinds of models. Otherwise, I'll see you all on Wednesday. Take care much.